Hello, everyone. In this episode, I'll talk about algorithmic collusion, the first one in the sequence. And this is based on Calvano et al. At American Economic Review. Um, and it's about two algorithmic sellers pricing using AI algorithms and how they end up colluding. Okay, let me just briefly show you the original paper. Okay. So this is the original paper if you're interested. It's Artificial Intelligence, Algorithmic Pricing, and Collusion by these people. And it's a simple idea. We have learned Q-learning in the past, and one of the reinforcement learning. And it basically shows you that two sellers relying on learning the opponent's strategy by looking at the prices and looking at the past prices, the authors find that eventually the algorithms end up charging prices that are above the perfect computation prices, meaning they tend to collude. Um, yeah, just to show you some of the key components, they do have some kind of Q-learning algorithm, as you know, that this is the basic Q-learning. Um, that's looking like this. And it sort of is related to the repeated game, of course, in economics. And if whatever they do have, like they charge the prices, um, the share that goes to the seller that charges lower prices get more of the market share end up being. Okay. And this is sort of what they do. Right? And what they do keep track of as a state is the past prices, past average prices that has been observed by each seller. So they try to do a Q-learning. I mean, two sellers do the Q-learning themselves by looking at the observed market price, average prices. Okay. So this is sort of what they do, and it does all kinds of parameters. For example, a good way to measure how the collision prices are, the Nash prices are typically the kind of competitive price that should be charged to benefit the consumers, and the monopolistic prices are probably the extra profit. In a theoretical sense, they can charge at most. So how much is the algorithm actually kind of charging? And it tends to be not quite monopoly price, but fair amount of it. And yeah, the authors try to carry this on the various parameters, and they can show it. Okay, so the extra price here normalized by the monopoly minus the Nash prices tend to be not zero, so they show that they exist collusion pricing. Okay. Okay, so let's get into the code. So here is a simple version of Calvano et al. Uh, what we do is that we do have two agents charging prices, and then I do have a central clearinghouse, a market price market maker, that basically goes to this downward sloping demand curve, A minus B average price. Okay, and the profit that each seller gets is the price minus the cost times the quantity they get assigned by these average prices. Let's see how that works out. Well, the first is as usual, basically just set up the Google Drive where I'm going to save the results. And you can see here there's a market demand and the market share, of course, to the lower charging price gets more market share. That's basically simple stuff. So this is kind of the simplest version of Calvano et al. Okay, so what we do have here is the market configuration, A minus B price bar, and the pricing grid. Okay, and the cost is normalized to be marginal cost is 0.5. Um, a lot of things here. And one of the things that we do is that the price is kind of the action choices when we have many bins. which are assigned into a array, meaning this is a Q table approach. So it will become, the action choice will become an index number of the array, which you have to convert back and forth from the index number of the price to an actual price we feed into the market, isn't it? So the price bucket, price from action, is basically doing that. The market clearing function is basically it takes the prices and then there's some random error, and then the demand is basically A minus BP bar, and then give the quantities Q1 and Q2 to the each respective seller who charged their prices. Okay, so this is what they have. Okay. And then there are two independent Q learners. You could, of course, program it like what we have done in Frozen separately, but it probably is convenient to have a data class and a class. So here what we do is a little bit sophisticated because we have two seller Q learning agents. So we just happen to create a class. We don't want to repeat the same thing again. So the Q agent here is it takes the states and actions and the configuration numbers here. And a random number, and then the Q table, of course, we're going to carry. And then we have fairly similar to Frozen, the epsilon greedy strategy. It's a little bit more sophisticated. We let it decay. Um, so it will do less exploration as it learns more and wants to get to the closer optimal answer. Um, and the action is basically the maximum Q action, or once in a while choose the random action. And then updating is, of course, our usual dumb Q learning action, that the particular chosen state and action, we change it to the Q table value. Okay, so this is our Q agent. Okay, so now we have the one-shot payoff. So it's price one, price two, P bar, and then they get um, the quantities of the profit basically for each respective sellers. And then we can train the two sellers. A1, create an agent, and A2, the second agent, and then initialize the average price. And then for period T, uh, we basically have the agent get the Q table, and then have a one-shot learning, and then the market um, will give you um, the profit, and then the agent updates, and it keeps doing it. Okay, so this is what the training looks like. It's a typical Q learning, except there are two Q learning agents that are interacting through the market. Just for reference purposes, the best response, meaning the Nash equilibrium response we can compute in this particular parameter choice, basically is 1.5 and 1.5, okay? And the mutual best responses could be 2, 2, or 3, 3. That's kind of when they fully collude, okay? So now you can basically run and save it. So we run this episode 300,000 times. Okay, so it's gonna take a few seconds. But you can see that we are basically calling the market configuration and then the train to sellers. So each time it runs an episode of that from the agents, and then basically keep log of this. So later on, we'll program print the average price and profits and save it to a folder. Okay. Yeah. Mm, so yeah. Okay. So the average price is 3.4 and whatnot. So this is sort of like what they created. Shall we take a look at it? Um, okay. So here, for example, the price they charge. Initially, they start and so and this is the learning period, but eventually they sort of learn to charge a lot. I guess at some point they drop to 3.5, and I think it's stabilizing here. Why is this happening? You can see this here. Initially, the two agent profits that look like it, they're competing back and forth and deviate and all this. And at one point, profit one seller kind of did it, but eventually, profit two, seller two realizes that it's been losing profit, so it charged the price. So eventually, they both charge this and be happy about it. Okay. So this is a simple algorithm computing. So now you can see that in the world of AI, the algorithms without even human intervention can learn themselves to collude, which is a recent debate in market regulations of all the Amazon and all these people selling their products through AIs. Okay. All right. This was about the um, algorithmic collusion. Thank you for watching this episode.